Well, thank you very much. We're certainly going to talk a little bit about UHPC and the sustainability aspects of that product, but I'm also more of a generalist today to talk about why it's important that we embrace sustainability in our businesses and why it frankly is important and why it matters. I'm not going to appeal to your heartstrings and say you need to do it for your grandkids. I want you to do it for your wallet, because it's part of the triple bottom line. People, planet, profit. If there's no profit in it, you're not going to do it. So there's a very good business case for being sustainable. This is a copywritten presentation. I can give you some slides if you want them. They just won't all be there. So Heidelberg Materials used to have a piece of Lehigh white cement. The only Lehigh cement in the country now is owned by an Italian company named Cementir. Not associated with Heidelberg Materials, not associated with me. That's a completely different company. Heidelberg converted 140 brands to the Heidelberg Materials name here in 2023. So in the Northwest here, it was Cadman and Ocean Cement. That's all Heidelberg Materials, et cetera. So, we're a big company, big in aggregate, big in cement, big in, pretty much solving heavy building material problems. That's what we do. And we're also fairly good size in concrete, ready-mix concrete as well. So let me re-push that button. So concrete, the reason why it's important to know all that is that concrete is a huge material as far as the world goes. We are the #1 building material globally, and more than 50% of everything we make in this world is concrete. Next to bagpipes, it is like #1. I love bagpipes. That's so cool. So, in any case, yeah, exactly. Let's crank up the bagpipes a little bit. So, concrete, even though it's more than 50% of everything we make, it has a carbon footprint of 7 or 8% of the world's greenhouse gases. Now, comparatively, that's small, but it's still a big number because greenhouse gases are a big deal. So we want to improve on that. So I've showed you this before. It's part of my mantra. Concrete is green. It's a sustainable product. You've seen it. So basically, this is laid out to where the heavier material is, and the less energy it takes and the less CO2 associated with it, those materials are down in the bottom left of the chart. The materials that take a lot of energy and have a lot of CO2 associated with them are going to be in the upper right hand of the chart. But you can see concrete's down here, precast is right here on this kidney bean shaped purple thing. Cement's here. Cement's a little bit more than timber, but timber's a lot more than concrete. Glass is way up here, steel. Anything you have to refine and is maybe light in weight is going to be way up on this chart. Very high carbon, very high energy to produce those materials. If I want to make concrete, I go out in a quarry, I pick up stone, I clean it off and make sure it's the right gradation. I combine it with some cement and I've got concrete. If I want to make carpet, I go to Saudi Arabia and I get some oil, and then I refine and refine and refine that product to eventually get to something I can use to make plastic, and then eventually that becomes carpet, right? So just think about the processing of a material. That tends to be a good rule of thumb of how sustainable a product is. So I touched on timber already. We're in timber country. Up the road here is the Tacoma Dome. At one time, it was the world's largest wooden roof structure in the world. I saw Sting there with police back in '83. That shows you how old I am, right? So timber's not going to replace concrete. If you wanted to replace concrete with timber, just 25% of that market, you would have to have a forest the size of the nation of India. And then you would have to harvest that, and then you would have to plant a new forest, and oh, by the way, you have to wait 30 years to harvest the tree again, right? So there's no real good alternative. So the key is to make our products more efficient, more effective, less carbon intensive. So when we talk about carbon intensity, we talk about how sustainable a product is, it is evaluated as essentially an accounting exercise. We count up all the impacts associated with the material, all the impacts associated with getting that material from the quarry. That's our A1 right here. A1 is over on the far left. That's our raw material extraction. A2 is our transport to the facility. A3 is the manufacturing. For cement, we're going to do that with the quarry. The quarry is our A1, right? That's our raw materials, our extraction. We're harvesting limestone because we need the calcium. We're harvesting shale or some other silica-bearing raw materials, a little bit of iron, a little bit of alumina, and that's our raw materials for cement. We're going to grind that up real fine. We're going to actually, let me back up one step. We're going to transport those raw materials to my factory. That's my A2, is the transport. A1 is the harvesting, A2 is the transport. And then I'm going to get it to the factory and I'm going to put it through my kiln. I'm going to grind it up real fine so that when it goes to the kiln and I raise it up to 2,800 degrees, that's my manufacture. That's my A3 in my life cycle. I'll come back to that so you don't have to memorize it, obviously. So 2,800 degrees is my target temperature. When I get up to those temperatures, I am releasing CO2. Calcium carbonate, which is limestone, is CaCO3. We grab the calcium, that combines with our silica, making up new compounds that are reactive when you grind them up. When they become cement clinker, we grind that up to become cement. The CO2 is released. Anytime you get above about 1,400 degrees Fahrenheit, you're releasing the CO2. It calcines right out. So that calcination of the limestone is a big piece of our emissions. So this is putting that A1 through A3 on a chart just to kind of give you the percentages. So my extraction is over here in my quarry. That's my A1. Transfer from the quarry to the plant. That's, you can see, I'm down around 3%. Very minimal impacts as far as my global warming potential, my carbon footprint, my embodied carbon for these materials. I'm using these terms all interchangeably. But the idea is how much CO2 is associated with that process. So very little back in the A1 and A2. For cement, it's my A3. That's my big impact, is in my manufacturing process. I take those raw materials, I grind them up in my raw mill, and then I put them through the kiln. About 25% of my emissions are the fuels I burn, right? I have to raise those temperatures up to 2,800 degrees or so. And then the CO2 that's released from the limestone, the calcination of the limestone, in this case, for this specific cement, is about 63%. It's about 2/3 is what we say. 60 to 70% of all the CO2 emitted from the cement comes from that chemical process. Then finally, I take that clinker, I cool it, I grind it up real fine to make cement out of it, and I store it. That's my cradle to my gate. My gate for cement is in the silo, ready to put in your truck to ship to you. In precast, the cement makes up about 75% of your carbon footprint associated with a mix. With a precast concrete mix, the green bar there is 75% is from me. I'm the cement guy, I bring the carbon to the party, right? That's my cross to bear. So that's why I need to improve my act and get better at reducing my CO2. I'll go through this in a little bit more detail later, but basically, you've got your transport from the quarry to your precast plant, bringing in the raw materials. That's about 7%, and then 15% is everything else. Okay, so as an industry, we recognize that we have this carbon, footprint. We recognize that we have this impression out in the public that we're the bad guys because we have CO2 associated with our cement. So what we've done is we've worked real hard at generating a roadmap or a plan so that we can reduce our carbon footprint. We worked with the Portland Cement Association and the Global Cement and Concrete Association, the GCCA, and we have come up with these different approaches. And essentially what we're doing is we're focusing on the clinker. We're reducing the amount of energy, that 25%, which is my fuel use, that CO2 associated with that. I need to get better at burning fuel. Need to get better at burning alternative fuels that aren't like fossil fuels, right? Instead of burning coal or pet coke or one of these other materials, if I burn, for instance, municipal waste, which is gonna rot and otherwise emit CO2, then I'm actually keeping that CO2 from getting released when I'm burning it, believe it or not. And then the other thing that we can do is we're going to reduce the amount of clinker in our cements. We talked about Portland limestone cements. Great first step. If you're buying federal white cement, guess what? You're using PLC. You know, it's very much like the type 1 that you had before. It's got up to 10% more limestone in it than the standard Portland, and we're helping reduce our CO2 in that way. We've reduced our clinker content, we reduce our CO2. And then, of course, we want to optimize our concrete. We want to get very good at that. And then we want to make sure that we design properly. And then the last thing we want to do is we want to account for carbonation. I'll touch on this more. So as an industry, we've responded. And as Heidelberg Materials, we're responding as well, right? So companies like ourselves have really worked hard at achieving these goals, getting better at making our clinker and getting better at making cements with alternative materials. So, like we say, we want to be the leader in this. We want to, Heidelberg Materials, I'm really pretty excited about being back with Heidelberg Materials because it was something that we always did. You guys know me for a long time. This has been a passion of mine, but Heidelberg Materials has really made it central to our business. It is no longer another thing we do. It is central to our business. So we're basically a tiger trying to change our stripes. We're no longer just a cement company. We're a materials company. And we've set some very ambitious goals. And one of these goals is to reduce our cementitious materials down so that we are only producing 400 kilograms of material, of CO2, excuse me, per ton of cementitious material. So essentially what that means is, don't get hung up on metric versus imperial units. Pound for pound, standard Portland cement has about 0.9 pounds of CO2 associated with every pound of cement. We're trying to get that down to 0.4, right? So 400 kg per metric ton's 1,000 kg, simple math. That's why I like to keep it in metric. All right, so that's a big ambitious goal. The other thing we're doing is we're going to produce about 50% of everything that we do is going to be a low carbon material. And this is by 2030. So these goals are very ambitious and they're coming up quick. About 6 years, this is all going to get done for us to declare victory and be able to put this behind us and say we've done it. The other thing we're going to do is we're embracing carbon capture, utilization, and storage. I'll tell you about that a little bit more detail, but essentially what that is doing is we're capturing that CO2 that we release from burning our fuels and calcining our limestone out of the stack. And instead of letting it go out into the atmosphere, we're capturing it, we're compressing it, and we're pumping it down in the ground for permanent storage. These goals and these plans have been certified by the Science Based Target Initiative. There's no agency out there that can say that you've got a good plan other than this SBTI. And this group, as you know, they formed a specialty group that understands cement, and they've gotten together and they've said, yep, Heidelberg, if you guys do what you say, you're going to get to your goals. So by 2050, we anticipate being net zero. So even though we're manufacturing cement and cement binder type materials, our emissions are going to be zero. The way we're going to do this is we're going to embrace innovative materials. We're going to embrace the circular economy. Think about recycled materials, fly ash, slag, recycled concrete. Concrete is you know, the material that keeps on giving. It shouldn't go to the landfill. It should get crushed up and used as space rock. You can use it back in and form new concrete with it, right? So then we're going to we're talked about carbon capture, utilization, and storage. And then we want to get credit for the natural carbonation that is happening with all concrete anyway. So we talked about measuring, we talked about accounting. And one of the big tools that we have in doing that is an environmental product declaration. EPDs there's an industry-wide, which we took part in, industry-wide EPD for cement, is published by the NRMCA. And this one right here is cradle to gate, of course, and this is where I got that number from. 922 kg of CO2 per ton of Portland cement. That's an industry average, right? And like we talked about over 500 kg of that is from that calcination, from that process emission associated with decarbonating the limestone. We talked about our whole building life cycle. Once again, just to be very clear, we're talking about this piece right here, the production stage of making that cement. That's what the A1 through A3 is, and that's where that 900 number comes from. So where where the rubber meets the road on this is when you start accounting for this, you start counting it up. So according to the EPD for architectural precast, they say that they've got this much cement in a typical ton of precast. And precast is a little bit unique. Instead of doing a square meter or a square foot or a cubic yard, they decided that they wanted to use a unit of a ton of precast material, which of course includes the rebar, which includes everything else that's in that precast concrete. In that, their mix calls for 143 kg. If you need to do the math, it's 2.2 pounds per kg, right? And they also said there's going to be a little Portland limestone cement in there. I'll talk about that later. But what happens is all of these add up. You multiply it out by your global warming potential. Remember, I told you it was 922. I multiply that out, and I come up with my total CO2 content or my global warming potential for that mix, right? So how am I going to reduce that? I'm going to reduce that by being more energy efficient. I'm going to reduce that by utilizing alternative fuels. I'm going to reduce that by converting to Portland limestone cements and using blended cements, which reduce my clinker content. I'm going to do that by embracing supplementary cementitious materials. Remember, I said I want to get to 400 kg of CO2 associated with all the binders I sell. Well, guess what? I'm selling fly ash, I'm selling slag, I'm selling alternative binders, which have very low CO2 associated with them. That's helping me reach my goal, right? And then, of course, we want to utilize good design. So, in a nutshell, when you start talking about cements, I've already talked about this a little bit before, but the clinker content is the key to how much CO2 you're going to have in your cement. Ordinary Portland cement with that big number, that 900 number, is that high because it has almost 95% clinker. That's the traditional Portland cement, which we all grew up using, right? So about 95% of that cement is clinker, right? 94, 95%. Portland limestone cement, I've dropped that down about 10, 12%, right? So my clinker content goes down, my global warming potential for that cement goes down. If I'm going to utilize a blended cement like they have right up the road here in Bellingham, we've developed a type 1T, which means it's a ternary blend, which means it has more than two things in it, right? I've got clinker, I've got fly ash, in this case, it's an SCM, in this case it happens to be a fly ash, and then I've got some limestone in there. That has a much lower clinker content. It has a very low carbon footprint associated with it, right? So that's the current technology. These are the things that we can do with cement currently to help us reduce it. I talked a little bit about SCMs. Heidelberg Materials this year will become the largest producer and seller of slag cement in North America. We're working with slag producers. We're putting in granulators, which is a key component to make slag reactive. And we're helping them develop those facilities. So we're going to be a huge slag supplier here in North America. Slag's a really great SEM because you can have very high replacements with slag. Fly ash people start about 15, 20%. Slag people start about 30 to 40% replacements, much higher replacement percentages with slag than you get with fly ash. And these, it's an air-cooled slag, doesn't do you any good. It's essentially a stone. It's not very reactive. When you quench it and you granulate it and you turn it into slag cement, it becomes very reactive. It's a very good SCM. The other thing we did is we purchased SEFA. SEFA stands for Southeast Fly Ash. SEFA is the largest fly ash producer in the Southeast, and they have developed the STAR process. And what that STAR process does is it takes the landfilled ash, which for decades has been put in landfills. It was a waste material. They would flood it so it doesn't fly away, right? That's where fly ash comes from. It's a coal ash material. It used to fly away, so that's why they call it fly ash. Well, Clean Air Act said, oh, you can't just let it fly away. You need to capture it. So what did they do? They put it in landfills, and then they developed a market for concrete, and they realized, hey, this stuff works great in concrete. Let's sell it to the concrete guys. We all started using it. That's been 20, 30 years, but they got way ahead of us in production. So there's over 1 billion tons, with a B, billion tons of landfilled ash in North America. That ash, when you pick it up, you harvest it and you run it through the STAR process, which reprocesses it and takes out all the carbon, the CO2 that's associated with that, or just the unburnt coal and fuel and stuff. Those materials become very consistent, very reactive. I was talking to the admixture guys yesterday. They really like it because it doesn't mess with your air, it doesn't mess with your admixtures. It tends to be a very, very good product in that way. And it tends to be very, consistent reactivity on that fly ash. Gary. Right, so Gary asked the question is how does these SCMs tend to be a dark color and they tend to affect your colors and those kind of things, how could they be used with architectural mixes because of the effect of that, right? So the answer is that yes, fly ash is certainly very dark. Fly ash is the fly ash through this STAR, because it's been burnt, tends to be a light tan. It's still not a white. Right? There are white SCMs that you can utilize. There are white silica fumes, there's metakaolin, and then slag cement is very light colored. It is it's almost, they used to, when I used to sell white cement, it used to piss me off because they'd take my jobs because they'd say, oh no, you just use slag and that'll work. And it did at times, certainly. So slag is very light colored. So that's a good option for architectural mixes as well. There's pumices out there. There's a number of different SCMs that you can utilize that reduce your cement content and don't screw up your color.
Consistent.
And yeah, they can be very consistent. Yeah, for sure.
On the topic of fly ash, I've got some samples coming in. I haven't really seen it yet, but I've heard good things about it. Micron 3 fly ash, I've heard is much paler and more consistent in color than the normal stuff. Is that true?
Let me make sure that you're getting some of that from us, because we do have a product just like that. Yeah.
Someone to get it from, we're in contact with a company right now, but yeah, we'll certainly talk.
I'd be glad to talk to you about that. But yeah, no, it does tend to be a little bit lighter. The one that we sell is from that STAR process, so it's a light buff. It is instead of an off gray, it's an off tan. But it is lighter than the traditional fly ashes tend to be quite dark gray. And they also, the consistency and color isn't there. But those processed ashes where they've really selected out and gone for the very fine particle do tend to be pretty consistent. So that is an option. And I'm sorry I didn't repeat that question. Go ahead there, Tim.
Maybe just kind of define the SCM for us.
They've asked me to repeat the question so that everyone can hear it, and I couldn't hear your question, Tim. I'm sorry. Can you?
The SCMs in the range for what is SCM?
Yeah, I am gonna touch on that through this presentation. So, launching into why SCMs work and the ranges of the different ones, let me jump onto the slide here. So, the way SCMs work is they bind up the calcium hydroxide, which is a hydration product, right? Fancy words. I learned that from a guy in the lab. So calcium hydroxide is essentially the extra calcium. When we sell a Portland cement or a Portland limestone cement, cementitious products, we typically talk about the different compounds within there. Calcium silicate compounds, right? We have C3A, calcium silicate, or calcium aluminate, right? C3, we've got three calcium, 1 alumina. We have C2S, 2 calcium, 1 silica. We have C3S, 3 calcium, 1 silica. You're getting the trend here, right? There's a lot of calcium. And the calcium works with the silica, it recombines, it makes calcium silicates, hydrates. That's my CSH that I'm talking about here on my slide. That calcium silicate hydrate naturally occurs within your Portland limestone cement and within your Portland cement. There's a lot of extra calcium. Calcium goes into solution, becomes calcium hydroxide, and these SCMs react with that calcium hydroxide, bind it up, fill the little capillaries that would otherwise be there, and tend to make your concrete stronger, denser, less pervious. So that's in general how all these materials work, right? And so the two big ones that we've talked about already tend to be slag cement, which is ground granulated blast furnace slag, or fly ashes. Those are the two big ones. There are a bunch of others out there. There's some new ones coming out in addition to the traditional ones. We've got biochar, which is a very interesting material I'm learning a little bit about. I used to be a naysayer, but I met a very talented professor out of the Colorado School of Mines, which changed my mind. This stuff can really react. It can be a good material. It is black. It is, wow. It is a very dark material. It is a char, right? It is essentially like a tiny little particle of charcoal. But depending on which material it comes from and what you've burnt to make that biochar, it can be reactive. There are ground glass pozzolans. They tend to be quite white. Remember the VCAS product? They used to be members of APA. It tends to be a very white product, so that can be very reactive as well. It's a silica, right? Glass is a silica-based material. And then there's calcined clays. Metakaolin is a calcined clay. We've taken a very high purity, high alumina clay, a kaolinite, which is as white as the tablecloths in front of you, and then we've calcined it. We've driven off whatever calcium is already in there, the CO2, and it's become reactive. That's how metakaolin works. Well, we've learned now that you can use much less reactive clays, and if you run them through a kiln or you flash calcine them and you combine them with Portland cement and some limestone, they make very good binders. They call this LC3 cements, limestone, calcine, clay, cement, LC3. And you're going to see that in your lifetime. We'll be selling those cements here in North America. It's just starting, it's just getting going. It's not a silver bullet, but it's a pretty cool technology, and we're going to be getting into that. And then, of course, there's lots of neat volcanic deposits out there. We talk about Roman concretes and stuff. A lot of those depended on these kind of volcanic ashes that were reactive, right? And with a lime type material. That's how those concretes were made. And that still works. The pummices and some of the other materials that are out there can really, the tufts, zeolites, there's a number of different materials that can really work well and be reactive.
How does that affect your efflorescence?
It tends to improve the efflorescence because you're binding up the calcium hydroxide, which is the thing that makes the efflorescence happen. Efflorescence, you need to defeat it. It's like I know, way to go, John. It's like a three-legged stool, right? So if you, for efflorescence to happen, you have capillaries that take the calcium hydroxide from the matrix within your concrete to the surface. And it reacts and carbonates at that surface and essentially makes new limestone. That's what the white efflorescence is. That's why it's that white color. On a dark background, you really see it, right? On a lighter background. People used to say, when I sold white cement, they said, oh, white cement doesn't efflorescence as much. And I said, oh, right, thank you, that's right, yeah. No, that's BS. It's just that it's a white background and you just don't see it as much. Calcium is calcium. When it hydrates, it looks just the same. So to defeat it, if you utilize these SCMs, they bind up that calcium hydroxide so it doesn't go into solution, so it doesn't end up getting into the capillaries and traveling. Plus, you're also binding it up by filling that capillary and closing that pore. And that's what sealers do. What sealers are doing is they're preventing that transport of the calcium hydroxide to the surface where it can carbonate and become new limestone. So if you can take away the chemical reaction by binding up the calcium hydroxide, or reducing the amount of transport of that through plugging up the capillaries, or just sealing that surface, those are the ways that you can defeat typically ready to do it. And we talked a little bit about UHPC. A key thing for hydration or looking at efflorescence on UHPC is to have some SCMs in there. A lot of UHPCs have a pretty high dose of silica fume and some of these other materials that will help defeat that. So that's kind of the key to doing that. Yes, sir.
So, two questions. One, in terms of the SEMs, and their whiteness and consistency, what would be your top choices? And then number two, are there any limitations in the amount that you can supplant with the PLCs versus the traditional Portland cement?
So Nick's talking about consistency of color, and he's talking about limitations, right, for the SCMs.
With the PLC, which already has them.
Yeah, there is no additional, there's no reduction in the amount of SCMs that you can use because you're using a PLC instead of a traditional Portland limestone, or traditional Portland cement. You actually get a better bump out of your early strengths with slag using a PLC than you do with ordinary Portland cement, because the limestone within there is ground superfine and it reacts with the alumina in the slag. So you actually get, if you were to side by side replace, say, 40% slag in a Portland cement mix and a Portland limestone cement mix, you'll get higher early strengths from the Portland limestone cement mix with that slag. Pretty much across the board that happens. As far as color consistency, slag cements tend to be very consistent, very good light colors. Metakaolin tends to be very consistent. It can have a bit of a tint to it. It can have a bit of a pinkish hue a lot of times, because that's just part of when they burn it, that when they calcine it and they heat it up, that tends to happen. Some of the pumices, Brian was here before. Remember, he was with one of those pumice companies that did it. They tend to be pretty good. But I would say that as far as color consistency, the slag and metakaolin for the light colored SCMs, those are probably the two. I haven't got a much. I know that there was John. You guys used the glass, the ground glass pozzolans before. What has your experience been with that as far as the consistency of color? I don't have a lot of experience with it. I don't know how to address that. Yes, sir, I am. It is, okay. Yeah, the color consistency then with the glass, I was asking John about that. So the color consistency with the glass, ground glass pozzolans tends to be pretty good.
Oh, yeah, totally.
Excellent. So there you go. So those are some good options for your SCMs. In addition to alternative SCMs, we're producing some very innovative materials. Chris Cox and Castone, they're doing a tremendous project with this TX Active material, which is a smog-eating cement. Sometimes we talk about it. It actually reacts with NOx in the atmosphere, reducing smog, very potent smog gas from the atmosphere. You actually pull it right out of the atmosphere. It reacts in that photocatalytic reaction, and you mitigate it right out of the air and you pull it right out. I've actually had a very interesting conversation in New Orleans where the professor is trying to test this. He thinks it also may give us a bump and an improvement in our CO2. It may also mitigate some CO2. That has not been qualified yet. But this is another innovative product that is we talked about tools in your tool bag. Gary was talking about tools in your case that you can go to. TX Active is another one of those tools And of course, it's, you know, it's real pretty. It's kind of fun. You know, the architects dig it because it's reducing smog. So it's a pretty neat product as well. And then I talked a little bit about carbonation, and this relates directly to our efflorescence question. So when we react, concrete will react with CO2 that's in the atmosphere. And like I talked about, when I calcine my limestone, I drive off that CO2. That is not a permanent reaction. That CO2 wants to recombine with that calcium that's there in that compound. That calcium silica compound wants to grab that CO2 back out of the atmosphere. And we've got this test where you utilize this dye, and it makes your concrete pink if it's not carbonated. Right? If I have not reabsorbed CO2 back into that concrete, it's going to be pink. You can see on the surface, I've taken calcium hydroxide and I've reacted with the CO2 out of the atmosphere and I've formed new calcium carbonate. Concrete actually gains weight in place. It actually gets heavier because it's absorbing CO2 right out of the atmosphere. And up to 50% of all the calcining CO2 that I emit in my cement process can be reabsorbed back into the concrete. We want to account for that because, once again, when people are counting carbons and they're wanting to point the finger at us, we want to say, hey, oh, by the way, we're also sequestering CO2 right out of the atmosphere with our concrete. So it's the same process as efflorescence. The difference is, instead of getting a very intense deposit of that material in a place where there was a capillary which forms efflorescence, this is throughout the entire matrix. And you don't see any color change. It will tend to whiten it up a little bit. It tends to lighten it out a little bit. But it's not, you don't get that efflorescence stain like you do. So carbon capture and storage is a different process. What I'm doing here is I'm taking the CO2 from my stack, and you can see this big, huge equipment. Here's the guy. This is a person. It's a person. He's 7 foot tall. I met him. He's a big, tall dude. Big equipment. Almost as big as the cement factory itself is what you need to capture the CO2 associated with the process, right? Same, size equipment essentially can be used for any industry, but this is the one that we're erecting in Brevik, Norway. Is the very first industrial scale carbon capture, utilization, and storage project in the world, and Heidelberg Materials is doing it. We're very proud of that. So we're going to sequester about 400,000 tons a year there. That will start, it's going to be active this year, the end of this year in 2024, and it'll be actually producing essentially net zero cement in 2025.
What are you going to do with the cap?
I'm going to pump it down into the ground and it's going to stay there forever. That's what I do with it. And I'll go into that a little bit more. So right now, we're actually taking orders. There are people who are buying this cement ahead of time, a year and a half ahead of time. They're giving us purchase orders for this cement so that they can have a net zero construction on their project, right? And so if you guys go online and you just Google CCUS, Heidelberg Materials, or just CCUS cement, it'll come up. There's a lot of great information on it. But essentially, the Evo Zero is the brand naming. That's our branded offering in this CCUS cements, and we're doing that in Norway. About half of our CO2 production in Norway will be captured, but then in Edmonton, Canada, we're going to capture all of the CO2. We're doing a bunch of these projects throughout the globe. We are not the only ones. We happen to be the first. We're way out ahead, but there are other cement companies doing this as well. So the cement industry is stepping up in a very big way. And oh, by the way, that's about $1 billion investment with a B. More like 1 billion, 1.2 billion, so $1,200 million investment essentially for just one of these plants. The one in Edmonton, Canada is going to be able to service. We've already figured it out that we're going to be able to service this market. So we'll be able to sell a net zero cement into Tacoma, into Puyallup, into Seattle, into the greater Northwest that will come out of Edmonton. And even with that transport distance, which is very great, we're going to do it on rail, you're still going to have a very, very low CO2 associated with this. So with this plant, it'll be a full 1 million tons. It'll be the entire process emissions that come out, all the emissions that come from the plant will be captured, compressed, injected in the ground. The reason we can do this in Edmonton is we have the right kind of geology. Can't do it in Florida, you can't do it in a lot of parts of the country. You have to have exactly the right kind of geology. So when you pump it in the ground, it stays there. Okay, so let me get away from cement and talk a lot more about precast. And all that is to set up the point of saying, when you guys are doing your precast, you know, when we're looking at it and we're looking up at that beautiful thing, how do we account for it? Well, the PCI has issued an industry-wide EPD, Environmental Product Declaration, for architectural precast. I'm going to use that as the example, right? So the EPD is based around a metric ton of precast. So you think about your precast panel, a metric ton, how many square feet does that work out? So what, about a half a yard, right? Maybe 0.4, 0.42, something like that. Cubic yards of concrete is about a metric ton. It's going to include all the reinforcing, it's going to include all the attachments, all the anchors, all of that material is included in that metric ton. That was the declared unit. I was not on that committee. I did not get a vote. Because I would have done it in square meter or square foot or cubic yard. But this is what they've done. For precast, your A1 through A3, you're taking my cement, that's part of your A1. That's your raw material that you're bringing into your plant. The A2 is the transport from the plant. So that transport I talk about all the way from Edmonton to here to giving you a net zero cement, that's part of your A2, right? And then your manufacturing is all the equipment, all the labor, everything you need to produce that precast panel or that precast element, that UHPC element that you're producing, right? It includes things like the steel, et cetera, right? And just as we talked about, cement is a small piece of the components in your mix, but it accounts for about 75% of your mix. Now, I know it's a busy chart, but here's the key, right? The central part of this is your production, handling and storage. They've got some weird stuff going on here because they didn't just say, oh, well, we're going to come up with a typical mix. They did a hard average. Well, because of that, they're saying, well, I'm going to use both PLC and ordinary Portland cement. That's not going to happen. You got one silo. You're going to put one material in. Your cement supplier is going to send you one thing. You're not going to have a silo of PLC and a silo of Portland. And oh, by the way, every conceivable admix that you can think of, all these guys are all admixtures, right? So the result is a little bit skewed, but it still is very good for illustrative purposes, right? The other thing that you'll see here is it includes welded wire. It includes steel. It includes the anchors, all the miscellaneous metals. Oh, and oh, by the way, it also includes some brick, and it includes some natural stone. And let's put some pigments in there, right? So all, that's why we have this big, long list. That's why this isn't a simple calculation, is that they took that average and they said, on average, everybody's got a tiny little bit of brick on their architectural precast panel. I can just picture the panel that they make, with this stuff. It would be scary. But it's good for comparative purposes. It's good to get a generic number. It tells us what kind of impacts we have. All right? So what that all boils down to is that the A1 is the raw materials that you bring into your plant, all those raw materials. Here's your transport to bring those materials to your plant. Here's your manufacturing. You can see disproportionately, the binder, the cement, is the thing that's carrying the carbon, right? That's where the big impacts are. That's why I need to improve my cement. That's why I need to lower my carbon footprint on my cement. That's why you get PLCs in the market, because we need to do that, okay? And you're gonna look at your global warming potential from your cement EPD to get what the carbon global warming potential is for that cement. You're gonna plug it in to a spreadsheet. I took the spreadsheet, and this is what I had to work last night. Take the spreadsheet, put it in here, and I've got basically just the concrete mixes. I left out the steel, I left out the anchors and the brick and all that other stuff, but I just wanted to give you guys the picture of the concrete, right? And you can see how many admixtures I got in here. I got air entraining, I got water reducing, I got accelerator and a retarder. I've got corrosion inhibiting. I have a high range and a VMA. And look, oh, by the way, this is the global warming potential of those materials. Big numbers, cement. This is an industry average, 922. This is Portland cement. You can see it's much less. The industry average for Portland cement, Portland limestone cement, I should say, is 946. That's a very simple demonstration of how I can reduce my CO2 associated with this, right? Look how much there is for the admixture. We're in the hundreds and hundreds, or even sometimes over 1,000. But the difference is it's so very small in quantity, it doesn't add up to much, okay? So when we do this, we put it all together. My A1 for my raw materials, my A2 for my bringing it here, my transport, you guys putting it in and manufacturing the concrete. A typical mix would be about 191 kilograms per ton, right, of concrete mix, right? All I have to do is I take these materials, I just change the numbers. All I'm doing is I'm gonna change the numbers at the top. Instead of a industry average, I'm gonna put in real numbers. This is what a type 3 cement out of Delta, British Columbia, which services this market. That type 3, instead of 922, is only 767. Big savings, right? The PLC I make from up there, instead of 800, it's 679. So this is a big efficient plant, has very good water access, has a low energy as far as electricity goes, very low CO2 associated with that electricity. So it's got a very low number. I put all these numbers together. If I utilize the Delta materials like we talked about, my A1 goes way down. It goes down to 123. So my carbon, my CO2 equivalent, which is the amount of carbon per ton in this case, goes down from 191, it goes down below 170. That's a 13% savings just by changing, instead of using an industry average, using a good quality, a very efficiently run cement plant in your mix. If instead I use the Bellingham, that blended cement, which I talked about, that has both fly ash in it and a little bit of limestone, and I use the PLC from there. And oh, by the way, I forgot to tell you, all of these mixes have a little bit of SCM in them. They all have a little bit of fly ash, because that's what was in the average. They've got 4.6 pounds of fly ash. Did I get it right? Oh no, 14.7 pounds. Add these all up. If I utilize that cement from Bellingham, which is a blended cement, which is, it's going to be a little bit slower setting, I'm going to lower my CO2 by 20%. So it's a big deal. If instead of doing that and getting exotic with these blended cements, I just use my type 3, right? Here's my GUL, I should say my type 1L out of Delta. And then I'm going to use slag. I'm going to use 40% slag replacement, which is very typical. I'm not going to use any ash. I have 0 pounds of ash in there, right? I'm going to add those up. I'm going to get a 37%, right? Simple math, folks. This is what it's all about. This is the power of an EPD. This is the power of changing up your cements. Okay, remember? We're 75%, that's a big one. Now, if I utilize carbon capture, utilization, and storage, that really changes, right? The cement is no longer the big boogeyman in the room. The CO2 goes down to almost nothing, and now it's a very small, small piece. And then we really can kick wood's ass because we're gonna have CO2 much less than that. Okay, so the other thing that's important that specifiers, stakeholders, owners, everybody gets on board and they understand this as well, right? We want to maximize our benefits by utilizing good design. And what's really neat about the precast industry is they typically come to you and say, I need a panel that does this. The ready-mix guys, they're told how many pounds of cement to use, they're told what the water-cement ratio should be and all this stuff, and it tends to be a lot of over-design. Our over-design comes from having to strip early, right, and having to get that out of the form. So we want to minimize that and be as efficient as we can with our concrete and make sure that we utilize, essentially as much as we can, recycled materials, et cetera, right? So UHPC, the way it becomes very sustainable is just like Anthony said, we're reducing our elements, we're reducing the amount of concrete that we make and use. Even though that concrete, because it has a very high SAC content, has a very high binder content, has a higher global warming potential pound for pound, you're using a lot less pounds. Like Gary was saying, you can reduce your weight dramatically. And when you do that, the overall effect is you're lowering your CO2. The other thing that's big is that you can make things really quickly, just like any precast. It fits right in with that. And it's going to have a very long service life, which will handle it. We talked a little bit about infrastructure, 50% less weight, 50% less steel, and all of this adds up to big savings. And carbon savings, and oh, by the way, if you can get those cars so that they're not stuck in traffic because you're trying to cast in place a bridge, you can have some huge savings in CO2. That's where the payoff is with UHPC, right? More durability. This is an award-winning job that just won a design award from the PCI, UHPC. And the idea is that it's going to be more durable, it's going to last, we're going to make it more resilient, it's safer, and of course all that adds up to sustainability, right? So specialty applications, things you can't do with other materials, you can now do with UHPC. Tim showed a very similar slide to this as far as marine applications. You don't have to worry about this stuff rusting out. You don't have to worry about it. You can go very, very thin. You can do very thin decks with it. You can do the perforated rain screens, thin shells, etc. These are all things that are very difficult to do with minimal amount of material. That's where the CO2 savings comes from. And then, cut down on your construction time, right? Less concrete volume. I don't know if I can say that enough. We want to reduce the volume. We want to be efficient with our concrete so that the CO2 that we've invested in that will pay off, right? Utilize SCMs. If your UHPC has SCMs in it, it will fluoresce less, and it will certainly have less carbon associated with that material than, say, an all cement mix. You can utilize lots of different materials of this, especially if you have control of your mix. So the key takeaways. We're under a lot of pressure in this industry to reduce our carbon footprint. You are too. It's not just me. There's enough pressure to go around, right? And the way that we are reacting is we are reducing our clinker contents, blended cements. We are getting more efficient about how we make our clinker, alternative fuels, right? We're embracing SCMs. I'm no longer just a cement company. I'm a materials company, and I'm going to sell you lots of different materials because that's going to lower my overall CO2 per ton of binder that I sell, right? That's a big move that people like us are taking. We utilize alternative materials. We're finding all kinds of uses for all kinds of materials that would otherwise use, in the old days, we just send them to the landfill. We can't afford to do that anymore. We want to get this under control. We want to embrace science-based target initiatives that will cap our heat gain to 1.5 C, right, by 2030. That, you know, I used to think that that was kind of an unattainable thing, but we can do it. We really can. Industry is responding, and you guys play a part in that because you make the coolest, prettiest, most, you know, carbon efficient material on Earth. And then, of course, you know, we're utilizing carbon capture, utilization, and storage. And I have a whole bunch of good stuff on that I can show you, Nick, as far as being able to capture that material. The cement that goes out the door is exactly the same. The difference is that my emissions get captured. And that's going to really help us solve this problem. So I appreciate your time, and I've got lots of good information. If you guys don't know me already, you can scan this QR code and get my contact. I'll give you a card. I'm still analog that way. I'm happy to give you a card. Nick.
Talk about carbon capture. I've heard of some products that are carbon capturing additives to the concrete. Is any of that in your?
Yeah, there's a number. Yeah, there's a number of ways to do that. I don't actually have a slide on that. I'm actually on the PCR, the Product Category Rule Committee for cements and concretes that they gain strength through carbonation, not through the hydration process of a Portland cement. They actually carbonate, and in that carbonation process, they gain strength. It's really useful in block and some of these other materials. You don't have to worry about your, you know, around the steel getting carbonated and worrying about the steel corroding, right? Because you're doing a block. And plus, block tends to be very porous, and so the atmospheric CO2 can get to it. So those materials tend to be, they utilize slags, they utilize ashes and other somewhat reactive materials that have already been processed and have driven off that CO2 and want to grab it back. So slags and those kind of materials that when they're heated up, the CO2 goes away from the process and they're going to recombine. So those materials are out there. There's some SCMs that come from some of these same companies that are doing this. I don't know as much about those, but there's certainly some materials out there, and I can get you some info and some producers. Most of that is in the masonry world. Most of that is for masonry units. And, you know, it makes sense. You don't have to worry about steel rusting or anything, right? And it's very porous. But if you do want to go to something like that, make sure that you've thought that through. We talked, I think it was Tim yesterday that talked about using glass bar, you know, GFRP, glass fiber reinforced polymer reinforcing instead of mild steel. You know, solutions like that, solutions like stainless steel, you know, in that way, it doesn't matter if you carbonate right down to the steel. You don't have to worry about that pacification zone. Can't say that right. You don't have to worry about the alkalis being reduced near the steel and it rusting. Right? You're utilizing a material that won't corrode. Well, thanks everybody. Appreciate your time, and be glad to talk to you.